Segment 49, the Hubble Law and Mapping the Universe. We've always spoken about the fact that distance is the hardest thing to measure, that we can measure position on the sky very easily, but that distance is very hard. Astronomers have struggled over many years to develop schemes for measuring the distance to objects at varying distances from the Earth, and we've built up what's called the distance pyramid. It starts with the fundamental measurements of the size of the solar system, which, as we discussed, relies on radar ranging, measuring the distance to Venus using the timing of the radar reflection, and then scaling from that distance to the Earth-Sun distance, the astronomical unit. From there, we use stellar parallax, the difference in the apparent position of an object on the sky as viewed from different sides of the Earth's orbit, as a very precise means of directly measuring distance to objects out to a few hundred parsecs. Beyond that, we rely on the fact that main sequence stars of the same spectral type have very close to the same luminosity to do a technique known as spectroscopic parallax, that is, measuring the spectrum of an object and then using that to infer its distance from knowing its luminosity. After that come the Cepheid variables, which are very bright and take us out into the realm of the nearby galaxies and even the nearby galaxy clusters. From that distance, we have to build on things that are even more that work at even larger distances, and these include using the rotation rates of galaxies, something called the Tully-Fisher method, and then using supernova type 1As that can be characterized in terms of their peak brightness based on the way they decline after that. Each of these methods builds on the method before it. So if you lay these out on a chart of distances, you'll notice that the different techniques overlap, and that gives us some confidence that the next technique, the one for the next larger distance, is actually working, because over the range where it intersects with the previous one, it's very effective. And this allows us to build out from scales of the size of our own solar system out to scales of several 100 million parsecs. So looking out for a substantial fraction of the size of the universe. Edwin Hubble, who was a prominent astronomer in the earlier part of the 20th century, used these standard candle techniques to try to determine the distances to galaxies, to try to get some idea of the scale of the local universe. And he made a very interesting plot in 1929 that looked like this. This is his original Hubble diagram. And what you see plotted along the x-axis is the distance of the object as measured by various standard candle techniques, in this case largely using Cepheid variables. And then along the y-axis you see the radial velocity of the galaxy, that is, its Doppler shift. And what you'll notice is that the nearby galaxies have pretty much random radial velocities. Some of them are positive and some of them are negative. But as you look to greater and greater distances, there's a very noticeable correlation. That is, the farther away a galaxy is, the larger its redshift, the more it's got a receding radial velocity. It's a velocity consistent with an object that's moving away from us. The modern version of the Hubble diagram looks like this. The little red box you see down at the corner is the size of Hubble's original diagram, and using different distance indicators, we've extended this out to vastly larger distances and vastly higher velocities. And as you see, once you get outside that box, the trend is very, very clear. The error bars get bigger at larger distances, but the trend is very, very clear. The farther away a galaxy is, the larger its redshift in kilometers a second. The slope of this line is what we call the Hubble constant. It relates the distance of an object from us to its velocity. Now, you would then naturally ask the question, is the farther something away from us, the more quickly it's moving away from us? Does this mean that the universe is expanding and that we're sitting at the center of it? Well, actually, the answer is no. And you can think of it a bit like this. If you imagine a jungle gym, and you assume that the galaxies are at the nodes of the jungle gym, at the places where the bars intersect, and then rather than simply expanding in some simple way, just imagine the bars getting larger. So the nodes are staying where they are, and the bars in between them are getting larger. when that happens, the node nearest to you will be moving away from you in any direction you look, independent of which node you start at. But the farther a node is from you, the faster it'll be moving away from you, because 2 bars are expanding, or 3 bars are expanding, or 4 bars are expanding, each by the same amount in each unit of time. So the nodes that are 3 or 4 bars away from you are moving away from you 3 or 4 times faster than the ones that are 1 bar away from you. And it doesn't matter which node you sit on and you look out at this, you see the same thing. If you imagine an infinite jungle gym and galaxies at all the nodes, each one will observe a Hubble diagram very much like the Hubble diagram we observe ourselves. What's happening here is the galaxies are not really moving. Space is expanding. Space is stretching. The redshift, interestingly, comes not from the objects moving away from us, but from the time that it takes the light to travel to us. Over that time, the fabric of the universe stretches, and the light waves stretch with them, and their wavelengths increase, so that the light, when it reaches us, appears to be redshifted. We can take the Hubble law and we can turn it around to make a diagram like the one you see here, where what's been done is to plot a slice through space, now just in one spatial coordinate and right ascension in a very thin declination slice, and put the distances onto this slice using the radial velocity. So using the Hubble law to get the distance from the radial velocity. And what you see is a very distinctive pattern. You see that the galaxies are not uniformly spread through the space, but rather are in the form of walls and lines. The walls are true physical structures that you're seeing here on the left and the right side of this plot. So this area over here, this bubble and the walls, and this area over here. The line you see up in the middle is something of a different beast, and we'll talk about that in the next couple of slides. So here is a cluster, a rich cluster of galaxies. These objects are bound together by gravity, and they're moving through space. They're moving through the universe, or sitting in the universe together, held together by gravity. So they're not expanding away from each other, but the whole group of them is expanding away from us. And because they're bound by gravity, they're moving in and out of the gravitational potential of their collective mass. And so they have motion towards and away that's not due to the Hubble expansion, but simply due to this internal mass that the cluster has. And that stretches out their appearance when you apply Hubble's law to this. So you have many galaxies in that stick in the middle of the diagram that are spread out in the distance direction just by their motion within the cluster, whereas in fact they're all at more or less the same distance. Much of the modern work on this subject has been done by the Sloan Digital Sky Survey, a survey of 1 million or so galaxies made by a telescope in New Mexico that's measured their positions on the sky and their redshift to allow much larger maps of the universe to be made. So here's a slice through the Sloan Digital Sky Survey showing again these beautiful bubble-shaped objects and huge walls that cover hundreds of megaparsecs. Each of the dots in this picture is an individual galaxy. This was made by then looking at space and then finding all the galaxies and measuring the redshift of each galaxy in that slice in space, like the ones in this picture. Now let's look at the Hubble equation and study it for a second. It says that the velocity that we measure is equal to some constant called the Hubble constant times the distance, where the Hubble constant is measured in kilometers per second per megaparsec, and the distance is in megaparsecs. The velocity is in kilometers per second. So what are the effective units of the Hubble constant? Let's analyze that. Kilometers is distance, seconds is time, megaparsecs is distance. So the constant, kilometers per second per megaparsec, you've got kilometers on the top, megaparsecs on the bottom. They cancel each other out. They're both distances, and you're left with a unit in 1 over time. The Hubble constant is in units of 1 over time. So 1 over the Hubble constant is a time. The current best value of the Hubble constant, measured by using the standard candles, is 72 kilometers per second per megaparsec. And if you propagate this through, 1 megaparsec is 3 times 10 to the 22 meters, and you divide through, you find that 1 over h is about 4.3 times 10 to the 17 seconds, or about 13.6 billion years. What does this mean? This means that if the universe were expanding at a constant speed for the last 13.6 billion years, it would have started as a singularity, as everything crushed together exactly 13.6 billion years ago. In fact, the universe does not expand at a constant speed, as we'll see when we talk about cosmology, but this is the characteristic age of the universe. And when people talk about the age of the universe, it's this 1 over h time that they're talking about.